let's talk about solutions of differential equations. So we have an example here. We'd like to check that y equals 1 over 16 times x to the fourth power is a solution to the differential equation that we see here. dy dx is equal to x square root of y. Okay, y to the 1/2 is square root of y on the entire real line. And so I use this notation here with a question mark, okay? So I'm not setting it equal. I'm checking that the left-hand side equals the right-hand side. So that's what I'm asking with this differential equation here. When y is equal to this expression, does this equation hold? With a question mark. So how do we do that? Well, we have the left-hand side, which I use LHS for. The left-hand side is just dy dx, so we just straightforwardly plug y into the left-hand side, and we end up getting 1/4 times x cubed. And now independently, we check the right-hand side. Okay, what's the right-hand side? The right-hand side is x square root of y. And so we plug in y into the right-hand side, and we get this expression here, which ends up being equal to 1/4 x cubed. Now, we ask the question, does the left-hand side equal the right-hand side on all of R, the real line? And the answer is yes, okay? So more formally, I kind of write this out explicitly just for the first example to just really kind of get at where we're going here. Does the right-hand side equal the left-hand side when we plug the relation into the differential equation that we have? Since the left-hand side is equal to the right-hand side when y equals that expression is plugged into the differential equation, okay, because the left-hand side equals the right-hand side, then y equals 1/16 x fourth is a solution to the differential equation. Furthermore, since both the solution and the differential equation are defined and valid for all of x from minus infinity to plus infinity, so all the real line, y is a solution on the entire real line. Okay, so just writing that out, the thought process, putting it in words, so we could do this much quicker in the future. Okay, let's look at another example. Is y equals 1/16 x to the fourth the only solution to dy dx? Okay, so we just found one. We can check that this is also a solution. Y is equal to parentheses 1/4 x squared plus 1 squared. Okay, and we do that the same exact way. We plug in if we plug in y from the left-hand side, we get that expression. We plug in y on the right-hand side, and we get that expression. They're both equal. Okay, so that is a solution. In fact, the left-hand side equals right-hand side whenever y is equal to this expression here for any c in the real line. So we could have plus 1, we had c equals 1 up there, but we could have c equals pi, or c equals 27, or c equals e, the transcendental number. Okay. And here, I actually give you a preview of one way to solve differential equations, which is called separation of variables, which we'll talk about, separable equations, which we'll talk about. And you could basically, integrate this equation, and we then see that this expression does indeed work, okay? We could have also just plugged in y into this differential equation with that expression, but I kind of wanted to give a preview of separable equations real quick, okay? Remark, notice that it was redundant to differentiate between C1 and C2. So in this step, so when I integrate the left-hand side, we're used to having that plus C for the antiderivative, okay? And a C2 there. If you move C1 to the right-hand side, you'll get C2 minus C1, and then you could also divide by 2 to get rid of that 1/2 there. Okay, so multiply by half or divide by 2. And so we call C this, but we could have also just skipped those steps and just wrote plus C at the very end, okay, because we knew that we're going to get a constant at the end, and as we'll see with initial value problems where you actually could fix that constant, what really matters is that you just have a C there, okay? Doesn't matter to differentiate between these different C's. At the end, we swept up the C's into just one grand C, okay? And so we do see that this works out. I do write here that C needs to be greater than or equal to 0, because otherwise, if C was negative, we got to take a square root of, we have a square root here. And we know that we can't take a square root of a real number and get a negative number, okay? So we're not working with any complex numbers here. And so we restrict ourselves to real numbers. Okay. Could there be other solutions? Well, this is a nonlinear equation with the square root of y, so always the answer to that question is tricky. But it turns out that if you have y equals 0, then yeah, the derivative of 0 is 0, and then x to the square root of 0 is 0, and so y equals 0 is a solution. I mean, here y equals 0 is not a point, it's a function. It's y of x equals 0, so for any x that you plug in the function, you get 0. It's just a constant function. And something to note here is that this solution could not be discovered as part of this family, okay? No matter what C that you put in here, you can't get 0 for all x, okay? So this is not, there's no way you could have gotten, if it was y is equal to C times that expression, then you could plug in C equals 0, and then you would get y equals 0. But here, there's no way to guarantee that y stays 0. You get the constant function. So that solution we had to inspect, okay? And something else to note is, when we did this separable equation here, when we solved this separable equation here, okay, at some point I did divide by square root of y, okay? And again, you always have to be careful when you divide by variables, because they can be 0 at some places. And when you divide by them, you make an implicit assumption that they're not going to be 0. And this causes you to lose some solutions, okay? Just to the listener who might have been confused and said, well, we did all of these steps pretty straightforwardly and we integrated. What happened? Why couldn't we get that solution? And I'm explaining here that at some point we did divide by square root of y. And that assumes y isn't equal to 0. And so it's not surprising that y equals 0 does not show up as part of that family. We'll talk more about these kind of solutions that show up as not part of the family. So let's give a formal definition for an ordinary differential equation. This sounds kind of strange, but again, let's be very formal at the beginning so we could relax more in the future. In any function, 5x, defined on an interval, so it's always important to talk about the function on the interval. You have an interval where the solution is valid. On interval I, in possessing at least n derivatives, okay, so that means that derivatives exist. They don't have singularities where there's some places where they're not defined on I. For example, 1 over x is not defined for x equals 0. So at least n derivatives that are continuous on I, which when substituted into an nth order ordinary differential equation Okay, and again, we're seeing the implicit form of the differential equation here. For all x and I, reduces the equation to an identity, is said to be a solution to the equation on. So that's what a solution is. Basically, that you have this explicit function, phi of x, you plug it in for y, and of course you take derivatives of it because the differential equation has derivatives in it, and you get an identity. It satisfies this equation, okay? That's what that's telling you there. An identity is, for example, like we saw up here, the identity that the left-hand side equals the right-hand side. And we'll actually make this very explicit to see how this definition works out. Reduces the differential equation. Okay, this is now a differential equation where f, and instead of writing x, y, and y prime, I use alpha, beta, gamma just to kind of drive home the point that this f is just a real valued function to the identity on I. And let's see what that means. So here, f is equal to x, y, y prime. So if we substitute, instead of alpha, we substitute x, instead of beta, we substitute y, and instead of gamma, we substitute y prime, okay, into this equation, right? This is our differential equation in implicit form. We get this, okay? And that's precisely the differential equation up here, okay? So just to show you what that implicit form looks like. And this reduces to the identity y. Well, we're going to plug in this solution. When we plug in this solution, so I take phi prime, okay, on the left-hand side, I'll have phi prime. So I distinguish between the left-hand side in pink and the right-hand side in blue. And so here's the left-hand side in pink. It becomes this when I plug in, just sort of symbolically plug in phi prime, and x wherever I saw a alpha, beta, gamma here, okay, and make that substitution. I still have that equation. And I then now substitute in phi of x, and I have this expression here. When I substitute phi of x, I simplify, and look, the left-hand side turns to 0. The 0 on the left-hand side is not, we don't presume that it's the same as the 0 on the right-hand side, but of course 0 equals 0. So we have an identity, okay? It didn't have to be the case that we got 0. So if we got 1 on the left-hand side, then we would say this wasn't reduced to an identity, and because 1 does not equal 0, this is not a solution, for example, okay? But the equation did end up reducing to an identity. That's what this kind of means. It's formal math speak. And so I just wanted to kind of be explicit about it here, okay? Because this notation is important for theorems, okay? And so because 0 equals 0, this is an identity, and phi is indeed a solution, okay? This just helps you understand what that definition is. Another definition, interval definition, the interval in which the solution phi of x to an ordinary differential equation is valid is called the interval definition, also sometimes called interval of existence, interval of validity, or domain of the solution, okay? For example, the entire real line minus infinity to infinity is the interval of definition for this solution to this differential equation. A trivial solution, okay, is a solution of a differential equation that is identically 0, okay, on an interval, okay? That's called the trivial solution. You hear that very often in mathematics. There's nothing trivial about the trivial solution, okay? It's just that it's y equals 0. And so we've called it trivial, but we still have to characterize it. And sometimes it's actually, the trivial solution is important, okay, for understanding, for example, systems of equations. So don't want to downplay it, but if you do have a solution that's identically 0, it is called trivial solution. So that y equals 0, for example, is the trivial solution. Solutions, like y equals 5x, may be expressed implicitly as g of xy equals 0. So the same way we expressed a differential equation implicitly, we could do the same thing with the solutions. So for example, if you define this function g of xy is equal to phi x minus y, or y minus phi x, then this relation here, setting that equal to 0, gives you your solution implicitly. Okay, now, and we do that for the solution y equals 1/16 x to the fourth, and we write g of xy is equal to 1/16 x to the fourth minus y, and we set it equal to 0. Okay. Now, all of this might seem trivial, and one might ask, well, what's the point of, if you already have y is equal to 1/16 x to the fourth, what's the point of writing it implicitly? Okay, and of course that's fair, and when you do have an explicit solution, well, you're going to go with that. But sometimes you can't get explicit solutions. Okay, sometimes it's difficult to characterize an entire solution curve explicitly. Okay, you can't solve for y as a function of x. And so this is very helpful, because whenever you have a function of two variables and you set it equal to a constant, what you're getting is basically a curve. Okay, whenever there's solutions, of course, sometimes there's never a solution, or a solution of a point, but in general, it's a curve. And so sometimes we're going to be forced to express our solutions to differential equations implicitly. Okay, and that's very common when we start talking about exact equations. Okay, just the way that we do those, we end up expressing solutions as level curves. Okay, level curves of functions of two variables, such as we're doing here. We're taking function of two variables x and we're setting it equal to 0, and so it's level because whatever comes out from the left hand side needs to equal 0. All right, so that's an implicit solution. What about an explicit? A solution in which the dependent variable is expressed solely in terms of the independent variable and constants is said to be an explicit solution. So you have y of x is equal to expression of only x. Okay, that's basically what a explicit solution is. Here, this is written, we wrote this implicitly up here, and we write the solution explicitly here. We have this phi of x. Okay. A relation gxy equals 0 is said to be an implicit solution of an ordinary differential equation on an interval, provided that there exists at least one function phi x that satisfies the relation as well as the differential equation on I. Okay, so that's why I was talking about all that, because we have this formal definition. Okay, this is best seen through an example. All right, so verify that x squared plus y squared equals 25 is an implicit solution of the differential equation dy dx is equal to negative x over y on the open interval negative 5 to 5. Okay, well, how do we verify? We just take derivatives. So we're going to take the implicit. We're going to differentiate implicitly. Okay, and that means we don't solve for y. If you solve, so you could solve, so someone could say, well, I could solve for y in terms of x. Not exactly. Okay, this is a circle. Circle is not a function. For a given x, you could get a positive value or a negative value. So you could have 25 plus square root 25 minus x squared, or minus. Okay, and so this is not a function. It's a circle. It's a relation, and so we're going to use implicit differentiation to check that regardless of where we are on this circle, we still satisfy the differential equation. And so we take the derivative of the left-hand side implicitly. When we do implicit differentiation, we treat x as the independent variable, y is the dependent variable. So what's the derivative of x squared? Just 2x. What's the derivative of y squared? It's not just 2y, because again, y is a function of x. Okay? X is just x, but y is a function of x. Y is a dependent variable. So we have to use the chain rule. So we get 2y prime times y. Okay? The outside function is squaring, right? And the inside function is y. And so that's why the chain rule gives you 2y prime times y. Okay? Taking the derivative of the outside function gives you 2y, and then of the inside function gives you y prime. And we could then solve for y prime, and we get this. And so, and of course, on the right-hand side, we had 25. Taking the derivative of that is 0. And so the differential equation is satisfied anywhere on the circle. Okay? Alternatively, we could have just looked at the top hemisphere of the circle or the bottom hemisphere of the circle. And again, I mean, this solution is a circle, okay? And so we could have just looked at the top and taken the derivative and checked that it satisfies. But we just, in one fell swoop, used the implicit differentiation to check the whole circle. Now, what does this tell us? Okay, this says that the relation, and this is a relation, we choose g of x, y as x squared plus y squared minus 25, okay? And we set that equal to 0, okay? So this whole circle is an implicit solution, y. Provided that there exists, so g of x equals y is said to be an implicit solution, provided that there exists at least one function 5x that satisfies the relation, as well as the differential equation. So we do need at least one function, okay? We can get a function. We could get all sorts of functions, in fact. I could have just said this works on the interval -5 to, I don't know, -4 or whatever. And that's a function because for any value of x, you only get one value of y. But here, I provide two different explicit solutions. One of them, phi 1 of x equal to positive square root 25 minus x squared, and phi 2 of x negative square root 25 minus x squared. Okay, so we can find on the implicit curve, we could find explicit solutions that satisfy the differential equation. Therefore, this implicit curve is an implicit solution to the differential equation. Okay? And here I explicitly write out what that f is, just because this definition uses it. And notice here, when we do put phi 1 or phi 2 into G, then we will get 0 at the end there. Okay, that's all that's saying there. So instead of y, we plug in phi 1. We could have done the same with 2. And with f, we do reduce down to an identity, so it's a solution. Okay, so we reduce down to an identity, and so we have an implicit solution. Again, just making this very formal. I mean, what's important is to check solutions at this stage, but it's also important to understand in mathematics why you make definitions formal. Because we're going to be proving some theorems, and if you look at just the gxy equals, this doesn't mean anything. So Now we have sort of an explicit construction of how to translate that definition into a specific example. That's what we're trying to do here. And I also remark here, not all solutions may be expressed in terms of elementary functions. Okay, so for example, this here, there's no antiderivative of e to the minus t squared. But you could leave it as an integral defined function by writing this. Okay, so this is a function of x because you integrate to x. And so it's not an elementary function. You can't express it in terms of like sines, cosines, sinh, cosh. And so that's just a remark, sort of tangent to what we were talking about. So let's look at another important definition, that of families of solutions. A solution of a first-order differential equation, written implicitly this way, containing a constant or a parameter, C, is a set of solutions, gx, y, c equals 0, called a one-parameter family of solutions. Okay, so this language doesn't seem so foreign thanks to the previous examples that we've done. A solution of an nth-order differential equation containing constants c1 through cn is a set of solutions, written implicitly this way, called an n-parameter family of solutions. So let's take a look at an example for this definition. We see here this solution, where c is greater than or equal to 0, is an explicit one-parameter family of the solution for this differential equation there. Okay. This is not one solution. This is a family. Why? Because c could vary infinitely. So for any c greater than or equal to 0, that's a new solution. So c could equal pi, 1.5, c could equal 27. Doesn't matter. Each one of those is a new solution. And so how do we group all of those solutions that could be obtained from this expression? Well, we group them. We call that grouping is called a one-parameter family of solutions. So here we have an explicit one-parameter family. We could also do this implicitly. So here we have an implicit solution to the differential equation, which we solved before, we looked at before. We checked that this is indeed an implicit solution. And we have a one-parameter family because the radius r could vary. Okay, as long as r is strictly greater than 0, you have yourself a solution. So r could equal 1, 27, or whatever. Okay, and each one of those is a solution, an implicit solution. For the second-order differential equation, we have a two-parameter family of solutions. Okay. We've checked that these two previously are solutions to their differential equations. Let's check that this is a solution to the second order differential equation. How do we do that? Well, we have the left-hand side. We take two derivatives of y minus 2 times one derivative of y plus y, because that's just what the left-hand side tells us to do. And we get 0. What's the right-hand side? The right-hand side is 0. 0 equals 0. Check. And so these are indeed solutions. And notice that regardless of what we just left C1, C2 there formally and worked with it. So we didn't fix it. We didn't say C1 must be greater than 0. So we just left it there. And we were still able to get that the left-hand side equals the right-hand side. In the language of this G that we see in the definition there, we would write G this way and just set that equal to 0. That characterizes that two-parameter family, okay? And so the idea of the n-parameter family is that you have these constants, okay? And specific solutions of these constants can be obtained by fixing the constants, okay? So specific solutions of the differential equation can be obtained by fixing the constants. Let's look at another definition, that of a particular solution, okay? A solution of a differential equation that is free of parameters or constants is called a particular solution. Now, what does that mean? It doesn't necessarily mean that you're, getting rid of them, that, this sort of family of solutions, somehow you eliminate it. It means that you fix the parameters, you fix the constants, okay? That's called a particular solution. So if we set c equals 0 in this solution here, that would be a particular solution, right? That would give us 1/16 x to the fourth. And so that would be considered a particular solution. Y is equal to 5x e to the x, where we took c1 here and set it equal to 0 and c2 equal to 5, is a particular solution of this second order differential equation. And just a note here that when we start talking about second order differential equations in the future, we'll break up a certain class of differential equations and their solutions to homogeneous and particular solutions. It's not exactly, contrary to this definition. It fits into it, but particular solution takes on a more specific meaning when we talk about particular versus homogeneous in the future. But for now, just see it as a particular solution being one where you fix the constants of the in-parameter family of solutions. A singular solution, what is that? Okay. A solution to an nth order differential equation that is not a member of the n-parameter family of solutions. That is, a singular solution is one that cannot be obtained by specializing or specifying or fixing any of the parameters of the family of solutions. So for example, y equals 0, okay? Not only is it a trivial solution, it's a singular solution as well, because we do get, by integrating as we've seen above, we do get a one parameter family of solutions. And no matter what c you put in there, you can't get y equals 0, okay? You cannot get y equals 0 for all x, no matter what c you put in there. Okay, so it's not part of that family. It's singular. What about a general solution? What is that? If every solution, and we emphasize every, if every solution of an nth order ODE, which is ordinary differential equation, written implicitly on an interval I, can be obtained from an n-parameter family. Okay, so here's our n-parameter family. You could think about it like this for that particular example. By appropriate choices of parameters, we say that the family is the general solution. So, if we have an n-parameter family, say this to the second order differential equation, if every single solution of this equation, this differential equation, if every single solution of that differential equation can be obtained by somehow fixing C1 or C2, then what we say here is that this is a general solution. Okay? It turns out that this is indeed the general solution. Okay? Every single solution to this second order differential equations can be obtained by fixing C1 and C2. We saw one of them here, but as long as it's a solution to this differential equation, you could somehow fix C1, choose appropriate C1 or C2 to get that solution. On the other hand, y is equal to 1/4 x squared plus c squared is not a general solution to this differential equation. Why? Because we found one solution where it's not a member of that family, of that one parameter family of solutions. So it's not a general solution. Remember, as long as you find one, then it can't be a general solution, okay? We love general solutions, right? I mean, if we have a general solution to a differential equation, it's like saying we found all solutions, okay? Sure, we have a constant or multiple constants, constant/parameter, call them either, that need to be fixed, but that's fine. We have the basic form, so we're happy. When we don't have a general solution, it's kind of trickier because solutions like this could pop out of unexpected places. And let's talk about solution curves, okay? So solution curves are basically graphs of solutions to the differential equations. We talked about the family of solutions for the differential equation here. We talked about that family. And we could fix that constant c, okay, to 0, and we get the solution here. When we plot that solution on the xy plane, it's called a curve, and so we get a solution curve. Here, of course, we have explicit solutions. We could fix c to 1, and then we get that solution curve. We could fix it to 2, and we get this, and on and on and on for any real number c greater than 0, greater than or equal to 0. We even have this solution here, y equals 0. We could do the same with implicit solutions. Here they're not functions, right? But these curves are solutions to these. As long as you're on this curve, you do satisfy the differential equation y prime is equal to negative x over y. Okay? And so here you see different solutions with different radii. All right? So all of these are solution curves to that differential equation. We also have, for the differential equation that we see here, we have a one parameter family, y is equal to cx to the fourth. That is a one parameter family of the one parameter family of the differential equation. Okay, solutions for the differential equation. And we could fix c. C equals 1, okay, is in pink over here. All right, that's what we'll get. That's just y is equal to x to the fourth, so that's a solution curve. If we choose c is equal to minus 1, we get the bottom curve there in orange. And now we could have what's called a piecewise defined solution, okay? So that along the interval, the function has different expressions. So here for x is greater than or equal to 0, we just have plus x to the fourth. And so it takes it looks like the pink solution on the right of the y-axis. And on the left of the y-axis, we take the orange curve, okay? And we glue them together, okay? So we glue these two curves together, the pink on the right-hand side and the orange on the left-hand side. We glue them together at x equals 0. And that is also a solution curve, okay? This is indeed a solution curve. And it's a singular solution, okay? Why is it a singular solution? Because we didn't take y is equal to c times x to the fourth and fix c, okay? We changed c. So c is positive 1 for x is greater than or equal to 0, and c is negative 1 for x is strictly less than 0. And so Gluing those two curves together gave us a piecewise defined solution that is also a singular solution.